for this conference, and it's really a pleasure to see as many participants. I think it's very good for category theory. And I would perhaps also just say a word about people who left category theory last year. I would perhaps like to thank them for what they have done. So Peter Hofstra, Martha Bunge, and Bill Lovier, I think we all owe a lot to them, and so I will dedicate my talk to them. And I'm not an expert in topos theory at all, but it's somehow nice that I could work on it thanks to Victor Duvagnac, so it's a joint work with him. And it is somehow related to the prehistory of topos theory. So I would like to speak about finite objects in toposes. Then about the pre-topos style by finite objects. Then about Galois categories. So this was a concept introduced by Grothendieck before he introduced toposes. Then about atomic Grothendieck toposes, and finally about profinite fundamental group. So the object is to understand what are finite objects in the topos. So you know what is, everyone knows what is a finite set. It's a finite sum of singletons. And for algebraic topologies, perhaps we are interested in finite coverings. So this is just a covering map with finite fibers. But what is a finite object in the topos? So, for instance, what is a finite channel on a topological space? And it's actually not an easy question, not an easy. And of course, there have been a lot of work on it, and somehow I would like to present a new definition of what a finite object in topos could be. So there is, if you have a Grothendieck topos, so which with a global section functor into sets, then it is very natural, and for in topology you do always this, to define what is a locally finite object. So you have a cover of the terminal object by some objects ui, and you want that if you restrict your object to these objects, you get a product of ui with a finite set. So ni copies of ui in some sense in the slice category. So this is a very natural notion of locally finite objects. But in topos theory, you have also somehow a geometric definition of what is finite. Namely, you can say that an object is decomposition-finite if it is a finite sum of connected objects, where connected means that you cannot cut it into two complementary objects in a non-trivial way. And so what I propose as definition of finite objects is to take the two concepts simultaneously. So as well locally finite, this is somehow as well decomposition-finite. So these are two conditions which are different. And in sets, they coincide, but it is somehow a coincidence that they coincide in sets. And the main theorem, perhaps I would like to give you some kind of sketch of proof of this main theorem, is that a connected Grothendieck topos is generated by these finite objects if and only if it is equivalent to the classifying topos of a profinite group. So this means to the category of continuous G sets for a profinite group. So that's more or less what I would like to present you today. And so I will a little bit review the notion of locally finite object, because this is a notion which has been studied also in topos theory. And there is Peter Johnstone who has introduced the notion of finite cardinal, and one can show that in a topos is a natural number object to be locally, so in a Grothendieck topos it is equivalent to be locally finite or to become a finite cardinal in Peter Johnstone's sense over a globally supported object. So there is a global average.
Not to me.
Okay. I meant it from you. But there is, so this notion of finite cardinal is valid in elementary topos with natural number object, but there is a notion which is valid in any elementary topos, and this is decidable Kuratowski finite. And in a Grothendieck topos, it's also equivalent to locally finite. So I think that this notion is due to Kuratowski for sets, but it has been introduced into topos theory by Courtois and Le Couturier and Nicholson. So in a very old paper. So somehow this shows that the notion of locally finite object is a very good one, because you can somehow generalize it in a correct way to elementary topos. And in an elementary topos, this natural number object, you can even, so what's the definition of Kuratowski finite? If you assume that your object is decidable, so this means that the singleton map factors through the classifier for complemented subobjects, then you can define Kuratowski finiteness by saying that if you extend the singleton map to the free monoid generated by X, it lands into the join similattice of the complementary subobject, and this must be an epimorphism. So this just means that you can generate X by singletons, and it was somehow Kuratowski's insight that this is a good notion of finiteness. And so in a special case of a sheaf on a topological space, local finiteness means just that the construction of the eta space over E is a finite covering, while decomposition-finiteness means that your finite covering space has only finitely many connected components. And you see these two conditions are very different. And so I try just to put them together into one condition, and I call an object finite if it satisfies both. There are several lemmas which are not all easy to prove, but which are very natural. So binary sums and binary products of finite objects are again finite. Complemented subobjects of finite objects are again finite. And the most difficult one is to show that the image of a morphism between finite objects is complementary. And here, the proof we use really uses Kuratowski finiteness. I cannot prove it directly with the local finiteness. So here somehow topos theoretical ideas are important. Now, these two properties shared by finite objects show that actually finite objects generate something which is a pre-topos. And so a pre-topos is not a topos, but it has somehow the most important, it shares the most important properties of a topos. So it's an exact category in the sense of Barr, and it's extensive. And I will say that the pre-topos is embedded in a topos if the inclusion is a full inclusion and is exact, so in the sense that it preserves finite limits and finite coordinates. And if you have a Grothendieck topos where the terminal object is finite, so it's automatically Kuratowski finite, but it's not automatically decomposition-finite, so you have to have a decomposition-finite terminal object. Then the full subcategory spanned by finite objects is an embedded pre-topos, and all subobjects are complemented. So this is somehow the starting point, is this observation. And it is very closely related to work of Acuna and Linton. So there are lecture notes, and I think it was some kind of workshop where this the analogous property was discussed for Kuratowski finite objects. But it is also true if you add decomposition finite. Now I will come to Galois categories. So Galois categories is some kind of axiomatization of Galois theory. And it has been done by Grothendieck in SGA 1. And it is a pre-topos in which all subobjects are complemented and which comes equipped with a functor into finite sets. So they call it a fundamental functor, I will call it fiber functor. And this functor must have two properties. It must be conservative and exact. So exact finite limit and colimit preserving. And so for any connected Grothendieck topos, the pre-topos spanned by finite objects is a Galois category. So we have seen it's a pre-topos. So now we have to construct the fiber function. And this is quite hard. And it is so I will try to give you a sketch of the construction of this fiber functor. And I must say that the ideas here are contained in an old paper by Michael Barr. Actually, two papers, Abstract Galois Theory 1 and 2. But his formalism is a little bit different, but the ideas are very similar. So what is important is the notion of a Galois object and actually of a splitting Galois object. So a Galois object is a principal bundle with in this sense that so it must be connected, globally supported, and the automorphism group of the object acts simply transitively on the fibers, more or less. That explains this automorphism. And a Galois object is said to split an object of your topos if x cross A is constant in the slice category. And the category of all objects which are split by a fixed Galois object is denoted split of A. And what is important is that this subcategory is actually a class C, fine topos of a finite group. So it's equivalent to the category of odd A sets, and say the map from odd A sets to a splitted object is the map which associates to odd A set M the fiber product with A over odd A. And so one can show that each connected object is contained in the smallest such splitting category, so you can associate to an object X what is called a Galois closure or a Galois cover or a Galois covering. So this is an object which lives over X, and it's a Galois object, and it's the smallest such one. So if you have which splits X, so if you have another one, then it factorizes via A. So this A is only determined up to isomorphism, and even worse, this isomorphism is not unique. So it is a feature of Galois theory that the objects are determined up to isomorphism, but the isomorphisms are not canonical. So you have to make choices. But you can recover your odd A set M intrinsically somehow as the set of morphisms of one Galois covering A into X. And this is given by an isomorphism which is quite well known. So X cross A is actually A cross this morphism set. So the morphism set shows you how many copies of A you need to build X of X cross A. And the second isomorphism is a canonical one. It is induced by the co-unit of the global section function. And then you can show that if you have an epimorphism from B to A, then the objects splitted by A are included in the objects splitted by B, and these two morphism sets are the same. So this shows you that actually the cardinality you need to have your trivialization is independent of the choice of A. Now this works well for connected objects. If you have objects which are not connected, then there is an additional choice you have to do, but also it is quite well known in Galois theory what you have to do. So if you have an object which splits into connected components, X, then you choose a Galois covering for each connected component. You take the product, and this product is not necessarily connected, but you take a connected component of this product of Galois coverings, and a Galois cover of these connected components, and this will split every xi, and so the morphism set from A to X actually is the sum of the morphism sets of AI to xi. And so the cardinalities are additive with respect to connected sums. And so this gives you some piece of the information that actually this cardinality functor, which is defined by E of A to X, that this preserves sums, so you have to also to show it that it preserves products, that it preserves co-equalizers, and that it is conservative. But all this can be done. So I will now relate Galois categories to atomic Grothendieck toposes. So an atomic Grothendieck topos is a locally connected topos, which is also Boolean. And and what is important is that in such a topos, every object is a sum of atoms. So an atom is a connected object, but it is more than that. It has only two subobjects, either 0 or itself. So this is perhaps the reason for the terminology atomic. Now there is something which is important in the Galois theoretical approach to topos theory, is that if you have pre-topos which is embedded in the topos, such that each object of this pre-topos is the sum of atoms, and these atoms form a set, then you can form the subcategory of sums of objects of P. And this will then be a Grothendieck topos, essentially by Giroud's theorem. So there is a very canonical sum completion of a pre-topos, and the inclusion of this subcategory is the inverse image of a geometric morphism. And now the theorem is that for any connected Grothendieck topos, the subcategory of sums of finite objects is an atomic Grothendieck topos, and moreover it is pointed. And the point, which I call here Galois point, is obtained by as the right adjoint of the fiber functor once you have completed it by sums. And you see, if you take sums of finite sets, you get the whole category of sets. So you have a subjective Galois point. The subjectivity is the fact that the fiber functor is conservative, and it is determined up to isomorphism, but not up to unique isomorphism. And so the automorphism group of this point carries a profinite topology, and the classifying topos of this automorphism group is precisely the subcategory of spanned by sums of finite objects. And this proposition has a quite easy proof. It's just that if you look at the finite connected objects, then you have an atomic topology on it, and it is quite easy to see that the sheaves on this side gives you back the sums of finite objects, and on the other hand, the sheaves on this side is the classifying topos of a profinite group. So this is quite classic. And now the definition is that the profinite fundamental group of a general connected Grothendieck topos is just the automorphism group of a Galois point. And so if E is finitely generated, it means precisely that E coincides with sums of finite objects. Then we have shown that it is classifying topos of a profinite group, and the converse result is very easy. As the examples, you can get now the profinite fundamental group of sheaves on topological space, and this is precisely the profinite completion of the classical fundamental group. Another example is if you take the étal side on the field, then the profinite fundamental group is precisely the Galois group of the separable closure of the field equipped with the Côte topology. So this gives some kind of common viewpoint of topological construction and algebraic construction. Thank you.
Good to see you. Thank you for this talk. If I ask you if you read my papers on Galois theory, I know that the answer is no. But have you read papers of John Kennison?
I have read the paper of Ike, and I know that Kennison was somehow in parallel with Ike. So I know what he has. I know what he has done.
Yeah, we'll talk later. Thank you very much.
Thanks for a very nice talk. I enjoyed it. But one thing that any topologist would say is that you want to make the fundamental group functorial, you have to pick a point in your space. So where do the points come in? You just talked about fundamental group or a connected topos, And of course, it's unique up to isomorphism. But the isomorphism only becomes canonical when you've chosen a point.
Yes.
How do you fit that into the picture?
You see, to some extent, I want to avoid choosing a point, because I think that Galois theory gives you, you have to make choices, but it gives you some kind of insight into what a point looks like. And then afterwards, exactly, one has to make it functorial. And so far, so I succeeded in making it functorial with respect to locally connected geometric morphisms. And so there is some restriction. It's not functorial in all geometric morphisms, because exactly if you take a general geometric morphism, it does not preserve Galois points. So you have a restriction because you have to preserve something. And I think that it's not a so bad situation. But I think that actually, for instance, étale homotopy is not dependent on the point you choose. So, of course, if you choose a point, then the functoriality becomes easier. But I think that there is something intrinsic if you have a connected Grothendieck topos. If it is not connected, then you should use group points. So, of course, then.
What's the link between the finite object and the fact that for the topos, which is and the coherent object inside of the topos? Because there should be somewhat related, no? Because the coherent object also form the topos, and coherent is somewhat related to uniqueness because of the compactness notation. So do you see they are related somewhere?
So I think that if your Grothendieck topos is finally generated, then it's the same thing, coherent objects. But perhaps there is also some work to do where finiteness is somehow replaced by cardinality conditions, and then one perhaps. So I think coherent is just the right generalization of finiteness. Perhaps one can mix it with some cardinalities.
Take the terminal geometric morphism from a topos, I can consider the pure entire factorization system, and then I think in this case we can prove, involving some theory, that the entire map will be classified by a profinite group point. Which means that I think what you're doing is presenting a different presentation of the entire topos that I get in the middle. And so I wanted to ask you whether this is reasonable?
I think so, yeah. But I think, so that this is something I would like to understand better. These different factorization systems, so these variations of monotone light factorization systems, and I must say I have not yet really understood it, but I think one should try to define a factorization system which gives precisely this and
it's the pure entire. I'm saying that it exists. Because also this answer a bit answers because the entire is a bit more than the
okay. But I would be happy if it is precisely the entire pure factorization, but I was not able to prove that. So.
All right, let's thank Clemens again.